Okay, so moving on to lab assignment 7. So we just finished up ANOVA, which, in some ways I think is a little bit more complex or harder to initially understand, like the different, like, post hoc tests, comparisons, the different values you have to pay attention to. Sometimes and like all the different rows, the between groups, within groups, all of that can be a little complicated. At least when you're less familiar with it, it just seems like a bunch of nonsense, which could be argued. So correlations, and this is kind of feed into regression a little bit, at least applying regression in a conceptual way, not actually completing a regression or running a regression in SPSS. So the correlations themselves are very easy to run, and pretty easy to understand, I think, in comparison in terms of the values you're getting and the interpretation. I have another data set for you guys. This data set, I didn't include a lot of context just because for this assignment I decided, you can pick what variables you want to include based on just maybe your interest or whatever. I wouldn't assume you can like generalize any like statistical findings from this just because, a very small sample. It was like 48 people. And this isn't, the whole data set. And again, I'm not framing the entire study. This is all correlation. Because we were running correlations, it's correlational. So no statistical, no cause and effect no statistical cause and effect can be like implied. As we know, correlation doesn't equal causation. So we're just going to be exploring the relationship between some of these variables. So literally the only criteria in your and as far as what you choose is it has to be, a combination of these continuous scale variables. So if you throw ID in there, that would be a problem. That's our identifier. It has no meaning outside of identifying that person's data. So as long as you don't put that in your correlations, you should be fine. So what you should do is pick 3 of the quantitative or scale continuous, however you want to phrase it, but pick one of these continuous or scaled variables of interest, so whatever interests you, to run correlations for. So initially what we want to do is some traditional Pearson correlations or bivariate correlations. And then what you're going to do is based on those initial correlations, you'll get an output table with those correlations, and I'll explain what to look for. But then based on the interpretation, choose a pair, so 2 variables that show either a noticeable positive or negative relationship. So it doesn't matter which way, but you should pick 2 that have whether or not they reach statistical significance. So, ideally one that is statistically significant, but if it's, trending in that direction, meaning it's getting closer to 0.05, but maybe not quite under 0.05, and it's showing a positive or negative relationship there, you could go with that as well. I'm saying that because I haven't actually looked, so I'll be running the correlations for this assignment, and then I'll, save it and ensure I have that information to compare against yours. But I actually haven't run the relationship. I haven't run these variables recently, so I have no idea if they're, they've reached statistical significance or not. So you'll choose a pair of variables that are either statistically significant, that interest you, or approaching significance, as we would say, or marginally significant. So maybe it's trending in that direction. And when I say trending, I don't mean like we're just making exceptions and saying, oh, because there's nothing significant, we'll go with this finding. It literally just means like when you're like running, especially a set of different variables, sometimes, your p-value is trending closer to the traditional significance threshold of 0.05. and sometimes it's like way off. So if you have say you have a p-value of like 0.3 something, 0.4 something, 0.5 something, like none of that is even close. Like I obviously wouldn't consider that even trending close. If something is like 0.06, 0.07, like it is getting in that direction, again, trending in that direction, you can't say it's statistically significant, but you can say it's trending or a marginal effect. Because also, depending on your significance level, like some people have again, less conservative significance level, so they choose a 0.1. That's not something I would consider like to change. Like the, standard in most research and publishing is going to be that 0.05, but I'm just saying it is possible to have different thresholds for significance. So you can say if something's like 0.06, you can say it's trending or marginally significant, as an example. And again, I'm just saying that because I don't know how many of these are actually significant. So essentially, based on the one you run, you should choose one that is either significant, that is interesting to you, or is, marginally significant or trending in that direction. As long as you don't pick a set of variables that are very clearly not related in this data, meaning they have like a very high p-value, it very well exceeds 0.05, then you'll get points for doing the scatter plot with those two variables. Pick a pair of variables based on the output from the correlations. And then next, what you're doing is running partial correlations. So partial correlations different from Pearson or bivariate correlations because it's bivariate, as it suggests, is it's examining the relationship between two variables. Partial correlations is now taking those two variables and seeing how that relationship changes if you control for a third variable. So again, it will show you the overall bivariate correlation, and then it will introduce the third variable as a control and then show you the new partial correlation. And finally, you'll have a result summary. And again, as usual, I've told you exactly what to include in terms of what should be reported when you're reporting correlations, like what numbers, what information should be reported. So as long as you stick to this, based on the output you get from these earlier steps, you're golden. And finally, part 5 is where we start making a conceptual connection to regression. So something to note about correlation. So we haven't done it before. A lot of the variables we've been working with, specifically our predictor variables, have been categorical or group variables, where we're testing or comparing the means across these different groups to see, is the mean of this group, whether it's high stress or low stress, high or low dose or placebo administration of vitamin C, so on and so forth. So we've been dealing with categorical independent variables or categorical predictor variables. And in that case, we want to use a t-test or a ANOVA because those are the types you use when you're comparing means across groups. However, what happens when you have a predictor that is not categorical and you want to see how one variable predicts another, but they're both continuous or they're both like scale items, such as amount of hours spent studying, amount of hours spent sleeping, stress levels, motivation in terms of it was, a scale that was used. And so we have some sort of like composite score of items. And the stress item, here it was on, I can just tell you, a Likert scale. So this was like more of a single item. But anyways, all this to say is you're using different continuous or scaled items that they don't have distinct groups, like whether it's gender or something you're experimentally manipulating, like vitamin C dosage, all that kind of stuff. Those are distinct groups, whereas like amount of hours spent studying, sleeping, or stress levels using a Likert scale, motivation using a Likert scale, or compositing those scale items, and GPA. Like all of those can be considered scaled or continuous items, which in this case we cannot use as predictors for an ANOVA or t-test because they're not distinct groups to test against one another. So instead, we're more interested in how these variables relate to one another in terms of when one variable increases, what happens to the other variable? How are they related? Are they positively or negatively related, and are they significantly related? So in this case, we use correlation and depending on what you're running, a regression. So the question is, when do we use one versus the other? And the answer is usually you want like a full-on regression model when you're trying to think of, especially directionality, when you're trying to think of how one variable is predicting another. So if you just want to see how two variables are related, correlation, that will tell you the relationship and if they're significantly related and what direction it's trending in, or what direction like that relationship is acting in. Whereas one variable increases, does another variable increase or decrease with it? And correlation does not imply like essentially precedence or what variable comes first. So it's not saying, oh, you know, say if I was doing, I don't know why this is open. If I was doing, you know, sleep and GPA, if I was saying, if I'm running a correlation, I can't say one is preceding the other or one is predicting the other. It's not telling you directionality. Now, maybe conceptually you can think about that and say, you know, you think you know what direction it's going in, but you can't statistically say that unless you run regression. So regression is using also continuous or scaled items, variables, to predict another continuous variable or another continuous outcome variable that you're looking at. So if you were treating GPA as your outcome variable, you want to see what variables are predicting this, and that is how you get some level of precedence. Correlation doesn't give you that. Okay, great. So, and usually when you're running a regression, you run correlations first, because before you get to the regression, you want to, determine, is a significant relationship even here? Even if I'm not like establishing precedence or cause and effect in any way, is a relationship here before I get to the point where I'm running a full-on regression model? You want to know if those variables are related. You do the same thing for like variables you introduce as controls. You see the correlations first, and then you move on to the regression, is typically how it goes in, research that you're publishing. So they're getting at very similar things in terms of, are these variables significantly related? However, regression, due to the test that is running, again, in the background, we're not thinking about regression for this class in terms of an equation or like what's going into that. So I'm not going to get into all of that, but just so you know, the information provided by regression, basically expands or builds upon correlation. Correlation is like the very bare bones to see, are these variables related? And then regression gives you more information as to how they are related. Now, when we get to this final question of connecting to regression, so obviously the context I just gave should help, but in general, you should, think about, look into, maybe test out running in a regression if you feel so inclined on your own. But essentially, you need to pay attention to what test statistics or what output you're getting from a regression that, again, goes above and beyond a correlation. Okay? So we're going to go over a correlation together, like the information you get from a correlation. And then you need to, using the context I provided and maybe some digging on your own, researching on your own, try and uncover what is the regression test or output providing that, you know, goes above and beyond what a correlation is providing. How do we run our correlations? So you may have done this in a previous class or just have done this before, but just to walk you through it, you're going to go to Analyze, Correlate, Bivariate. And this is where you get the Pearson correlation, so it should already be checked. And again, you're just picking three variables, three of these quantitative variables of interest. I'm throwing them all in here. But you just need to pick three, and you can go to Options and check means and standard deviations because you want those descriptives as well. Always when reporting, you want those descriptives to report as well. And then just make sure two-tailed is checked, which is definitely noted in the assignment details. But again, when I open this up, these were automatically checked. It would be very surprising if they weren't, just because these are the most commonly used. But if they're not, just make sure these two are the options that are checked. And then correlation coefficients, it's like you don't have to pick one, so you can check off multiple. But for the purpose of this assignment, you really just need Pearson. So then you would hit OK. So then in your output, you'll get a correlation. You'll get the descriptive tables, which you need, both for your output and your write-up. And then you'll get your correlations table, or the kind of matrix, as some would call it, with the way it's set up. So what you're going to see here is it's comparing each variable that you put in the variables box when selecting what to put in your correlations. So it's taking each variable and testing it against the other. And then the way the matrix is set up, it will be tested against itself. But something you'll see, for example, is that the values, when they're tested against each other, in some softwares I've seen it show up and it's, they put dashes to show like, oh, don't compare these two, like you're comparing it against itself, or it just has a correlation of like 1. So that correlation coefficient, the Pearson correlation, will be 1, showing, hey, these are the same thing. You're comparing the same thing. And then it will always be, if it's reporting a 1, like a correlation coefficient of 1, this Pearson correlation, then it will always be significant because it's saying, yeah, they are highly related, but it's because it's literally comparing the same variable against one another. And that's just the way the output tables are usually set up. But like I said, some softwares automatically for you puts like a dash, so you know, like, hey, skip over this one. Then what you can do is go, okay, GPA against study hours, GPA against sleep hours, stress, motivation, like so on and so forth. And really the information you're getting here, so you have the correlation coefficient, you have the significance or the p-value, and then n. So basically how many in the sample are being used to determine this relationship. And the reason this is important is if you have like missing data for some variables, obviously the n for a specific comparison with that variable with missing data is going to be lower than other variables who maybe didn't have any missing data. So let's say GPA has, full data for all cases. So 48, we have all GPA data for all 48 people in the sample. So that n will be 48. But say motivation for some reason, like maybe someone skipped or was an outlier, so we are excluding that, whatever it may be. Sometimes you genuinely just have missing data from like someone skipping a question, or you can tell they, if you put in an attention check, like a way to check like, okay, are they actually like reading the question? And so you determine like, oh, they weren't paying attention and they just checked whatever. So you exclude their data, whatever it may be. Or sometimes again, questions are accidentally or purposefully skipped. Whatever it may be, some variables may have a lower reporting rate than other variables, whether due to accident or intention from the participant, whatever it may be. So when comparing, say, if motivation had some missing data, motivation and GPA, the N would be lower because there's only, say, 40 cases where we have data on motivation. So therefore, those additional 8 cases that are missing motivation data can't be compared to GPA. Like there's nothing there. So it's going to exclude that from the comparison. So the N would be smaller. I don't think you'll have anything to note in terms of differing like ends for different comparisons here. The data is complete, so nothing to worry about there, but I'm just letting you know that's why it's included. So it might seem redundant, like, why do we need to know the N? Like, maybe it's more clear here. Like, we have 48 cases of reporting on each variable, right? And when we're using like categorical variables, this is really to help us make sure we have an even balance in terms of, okay, the same number of people were assigned to, or relatively the same people were assigned to group 1s, 2, and 3. But this is for continuous variables, it's often more the case of like some variables have missing data for whatever reason. So then a specific comparison will have a lower N because of one of those variables having missing data. That's the Pearson correlation tables you need, and that's the information you're getting. So the correlation coefficient, hopefully this is a refresher, but this is what is used to determine the direction and magnitude of the relationship. So it's telling us in what direction, positive or negative. So positive coefficient, positive relationship, negative coefficient, negative relationship. And not in terms of positive, good, negative, bad, but in terms of as one variable increases, what happens to the other variable. So as GPA increases, if it's a positive relationship, study hours will also increase. If it's a negative relationship, as GPA increases, study hours would decrease, which would be really surprising. But yeah, so that is telling you both the direction and the kind of magnitude of the relationship. So is it a small correlation, moderate, strong? And that is referring to how, so the actual value. So how close to 0 the correlation coefficient is, or how close to 1. As I mentioned, when you're in the table, when you're comparing like GPA to GPA, same table, you'll get a correlation coefficient of 1, which, is not a meaningful correlation coefficient. If you ever have a correlation coefficient of 1, it's honestly a huge red flag, because essentially that should be telling you that you're comparing possibly the same variable. In this case, literally the same variable, but sometimes maybe you have different quote unquote variables, like they're labeled different things. But there are times when maybe you're inadvertently capturing the same thing with like 2 different variables. So say maybe if you were using like 2 different stress scales, you would expect those, if they are measuring the same like facets of stress, or the same aspects of stress, if they're approaching stress in a similar way, in terms of what they're asking, what specific items, are they asking about, maybe more subjective, like I feel really stressed right now, versus maybe more physical symptoms of like anxiety or something like that. So if you had, say, 2 different stress scales and they were like had a 1.0 correlation coefficient or Pearson correlation, that would suggest you're essentially measuring the same thing, even if they're labeled as different variables. So any sort of correlation coefficient that is that high in terms of 1.0, or even like really high, like 0.9, 0.95, like anything really high like that, sometimes is, gives us kind of check to pause and be like, are we actually capturing different variables here? Or should we even be trying to correlate these because they're essentially the same? Like, should we be trying to establish a correlation between 2 variables that are essentially measuring the same thing? No. it's like obvious. If we're essentially measuring the same thing, of course the scores are highly related to one another. Just to summarize there, if the correlation coefficients are extremely, extremely high, like very close to 1, that would be something concerning. But in general, this number is giving you an idea of the strength of the relationship. So not necessarily the direction. The direction comes from whether or not the coefficient is positive or negative, but the strength of the relationship. And even when say the correlation coefficient is smaller, so say something around 0.2, so not a very like large coefficient in terms of how close it is to 1, but the significance is, or the p-value is what tells us whether or not that relationship is significant or just due to chance. But if the relationship is significant, you can still have a significant small correlation. Like small correlations are, they exist everywhere. Not everything has to be like very highly related to one another to tell us something important or interesting about that relationship. So that's something to think about in terms of what you're reporting. So obviously you need both the correlation and coefficient and the p-value to report the overall correlation. Was it significant? What direction is it in? And is it like a small, moderate, or strong relationship from this information? That covers the bivariate correlations we needed to run. However, now we need to run a partial correlation. So I think the most famous example that I've heard in, most research methods class or just in general when learning about correlations or relationships between variables, the best example I can think of, and again, maybe you've heard it before, it's a very stereotypical example given in classes, I feel. Stereotypical not in a bad way, it illustrates the point very well. But the reason maybe you want to run a partial correlation is in instances where you want to examine the relationship between two variables while accounting for the influence of a third variable. And this is very important when we're looking in correlations because, again, we cannot infer precedence. We cannot eliminate the possibility of some other explanation. We cannot infer causation. So while we can say two variables are related, that really doesn't necessarily mean a lot when we're looking at two variables alone sometimes. Because while two variables can be related, that doesn't mean that one is causing the other. Like something else could be causing both of them entirely that we're completely missing or not considering. And the cliche example I'll give is ice cream sales. Sorry, I'm trying not to butcher it. Ice cream sales are very highly, like strongly positively correlated with crime rates, if you can believe it. And that may seem odd, and that's because there's an entirely third variable that is really contributing to both of those variables. But when we just look at them together, we just see a strong positive correlation. When ice cream sales are high, we also see higher crime rates. But in the wrong hands, with the wrong interpretation, that can be, run away with. And we say, wow, when committing crimes, do people just go buy ice cream? I don't know. Or like, why are these two things related? And the third variable that, we should be considering here is relative temperature or climate. So in times of higher temperature, so increased heat, we see both higher ice cream sales and higher crime rates. The ice cream sales and crime rates themselves, while they're positively correlated and they show statistical significance, that's not because one is causing the other. It's because of a mysterious third thing that sometimes it's very easy to miss, like confound or a third variable that could be explaining the two when you're just honed in on those two. You just see a strong significant correlation. But that is why correlation we have to be very careful with in terms of our interpretation. We can never, just because things are positively correlated doesn't mean that one is influencing the other. And that is the reason why we might want to introduce a partial correlation, because if we look at ice cream sales and crime rates, we'll see a significant positive correlation and a moderately to strong one. But if we do a partial correlation, we'll see, we'll get that bivariate correlation information, but then we can introduce that third variable of heat or temperature outside, and then we can examine the relationship between ice cream sales and crime rates while accounting for the influence or relationship of temperature outside. So what this will do is then basically eliminate the positive significant correlation we see between the two, because once we account for temperature outside, that relationship between ice cream sales and crime rates has been explained. Like, there's no more, we've accounted for the variable that is actually contributing to both of these, and therefore the relationship, when we get that partial correlation information, that relationship will disappear. And that's just one example. There may be other examples where accounting for an additional third variable strengthens the relationship between two variables. There are different instances of why that's important, but essentially what you need to know is partial correlations introduce a third variable to control for, to then examine the relationship between two variables while accounting for the third variable, to say, okay, if we control for temperature outside, is there still a relationship between ice cream sales and crime rates? And in that case, the answer is no. There's no actual, influence of ice cream sales on crime or influence of crime on ice cream sales. So once we account for this third variable, the relationship disappears. So that's why partial correlations are useful. And in terms of, this assignment, I will let you, decide which third variable you introduce into the correlation of interest that you examine. But essentially what you need to do is go to correlate partial this time, and you're going to put in the variables you're interested in examining, and then put your third variable in this box. So I'm leaving that up to you. You want to make sure two-tailed is still checked, and then we need our means and standard deviations again. So in this box, you're going to put the variables, the correlation that you're examining further, while accounting for whatever third variable you choose. So that'll be up to you. And then the other part of the assignment in SPSS, which we have definitely done before, but just creating a scatter plot. So that is just a means of going to graphs, legacy dialogues, scatter and dot. And I would do simple scatter, and then you just need to plot one of the variables on the x-axis, one of the variables on the y-axis. And in this case, I personally don't have like a requirement for what you put where. As we have discussed, for correlations, we can infer which one is, if one is causing the other, if one is preceding the other, we can infer that from just correlations. And also there could be another third variable that is influencing both of them. So which one you put on the x versus y axis should not be interpreted as one predicting another, essentially. So that's why I don't have any requirement about which one you put where. So whatever relationship you're examining, I'm not saying it's not, okay, well, you have to put study hours in the x-axis, or, vice versa. So that's up to you, but you just need to plot those two variables with a scatter plot. So I showed you, I believe, using legacy dialogues, but there's also the chart builder, and you do scatter Again, you drag that here, and then you would drag your variables of interest to the axis. Okay, so that's all I need to show you in SPSS. So just be sure to pay attention to the assignment details as far as what needs to be present in your output as far as tables, but it's pretty standard for what we've been doing all semester, which is the actual result of the statistical test you're running, the table that comes with that, in this case a matrix, the correlation matrix, and then the descriptives. And then you need your scatter plot. So just as long as you're following along with the assignment details, you should be golden. For the partial correlations, you'll get both the bivariate or that original like Pearson correlation as well as the partial correlation once controlling for that third variable you introduce. And then the significance levels, of course, the p-values. Then you'll have your results summary. So in your text box, writing up the results, and I've included everything that should be in the write-up, everything that should be reported, as well as the general format of how that's presented. And then part 5, as we already discussed, is really just more conceptual thought exercise, getting you to think critically about the difference between correlation and regression, and again, what regression adds in terms of prediction power, or however you want to put it. So what is regression? Essentially, why don't we always just run correlation? What output, what information is the regression providing that is above and beyond a correlation, is essentially how I would think about it. So again, what is the purpose of not always just running a correlation? Why do we need a regression? Why is a regression useful? Why is a regression adding information above and beyond a correlation? As usual, you're submitting an output file with all of the following. And again, this one is also worth for up to 20 extra credit points. And just be sure you submit by December 6th, whether you're going with one of the extra credit assignments or both. Whichever ones you choose to complete just need to be submitted by December 6th. If you have stayed to the very end of the very last lab video, I have chosen to subject you to photos of my dogs. This girl is Stevie. His name is Bo. And this is Phoebe. I rescued them all in Oklahoma, since I've been in grad school at OSU. And inspiration for their names. Stevie was Stevie Nicks. She's all black, kind of a witchy vibe. Phoebe is the kind of sad girl out of all of them. She's very much a crybaby, very dramatic, very woe is me. And she was named after Phoebe Bridgers, who, if you listen to Phoebe Bridgers' music, very sad, so very fitting. And then Bo, well, he's named after Bo Burnham, and the only context I can give to where that came from is it just makes sense. This is a silly guy right here. Silly, but very sweet guy. Anyways, it was a pleasure working with you all this semester. I really enjoyed seeing you guys develop and, incorporate feedback, whether it was for SPSS lab assignments or the research project. I just really admired how you guys, were really receptive and open and wanted that feedback and truly did something with it. You will not see me post another lab video, but please reach out if you have questions. You can email me, you can come to office hours, you can schedule a time to meet with me. Still readily available until the end of the semester. You'll see some additional feedback from me in the coming days, as well as on any of the extra credit assignments that you submit and the final research project. Typically with the final project, because it's at the end and they need to be graded quickly because all of you, need your grades submitted, the feedback on the final thing is usually less than the feedback you've been seeing maybe on the individual assignments. But that also makes sense because you've already received detailed feedback on these individual components. This is really a matter of putting them together, incorporating some revisions. So, if you have any questions about your final research project grade, feel free to reach out, but just know that typically, feedback, especially as you improve the assignment, as you improve, you're going to see less feedback in general, but also at the end of the semester, you guys want your grades, of course. So I wish you all the best, wishing you a great Thanksgiving break. Please reach out if you need anything. Good luck.